Okay, so let's look at a problem that we want to solve with the graph. So this is a very famous data set, sad but famous. With the list of passengers from the Titanic ship. So basically, there's a lot of properties in the data set, but many of them are redundant. So here we have a simplified version of it, which has class, age, sex, and survivor status. The basic idea, I mean, of course, you could do any prediction, but the basic idea is to predict survivor status from the other three. So in here, I don't want to deal with the missing imputation, kind of as a separate issue. So I'm just gonna delete the missing data here, and this means basically delete the rows when a column is missing. Yeah, so delete at level 1 when something is missing on level 2. So here this Titanic data is now full square table of data. I have some quantities. So if I take this and I do normal, come on. You see this quantity here in years. We could say, okay, this is a numerical value with some decorator, and there's like 3 categorical variables, like discrete. Yeah, class is first, second, third. Sex in this dataset is female and male, and survivor status is survived or died. So if I want to use this thing directly, we need to massage this a bit using encoders. Then we want to do, I have no prior assumption about how the shape of the feature should be. So we are going to add some generic feature structures, and then we are going to use our binary classifier in this case to decide, or at least indifferent in this case. There are 2 classes, so it's always binary, to decide if it's survival, the specific sample person has survived or died. Okay, let's put all together. So in this case here, I'm gonna basically, let's start from the end. I'm using encoders for class, class, and for the sex class. And here I'm specifying, male, female, first, second, third, taken from the dataset. I'm saying here indicator vector, which I think is the default, but probably overspecified this. So this is the one hot encoding, like 100. Oh yeah, because the class encoder, the decoder goes from probability to label, and this one here, you have choices. You can go from the label to an index, 1, 2, 3, 4, or from the label to the one hot encoding. And I just want to make sure that this is one hot encoding. For the age, I could clean up the dataset beforehand, but I just want to, cram as much stuff as possible in my network, because this way I can just throw it at my already formatted data. I'm using a generic function encoder, and I'm using the function quantity magnitude. This is basically taking away age from the number. And I'm just telling for the inference, the size inference, that this is going to be a real number. And then I'm using another decoder in this case on the output, which is again a class decoder, and is a survivor status, which is survived or died. You see here that I use the same name here as my keys in my columns in the dataset. This way I can use it in NetTrain without actually reshaping things. Okay, now let's look at how actually we create the network here. So here I basically already split this in parts. I embed, I take this indicator vector and I project it to a five-dimensional space. And I also do that for the age. This is like slightly redundant, but I like the symmetry of having the same amount of features for each original features of the input. So you have I have 5 real numbers for sex, 5 for class, and 5 for age. which are created from the numeric representation. And then I combine them using this concatenation. So basically, this takes 3 vectors and makes them of length 5 and make them a single vector of length 15. And now this is my feature. Yeah, I mean, this distinction between what is feature extraction and what is classification is a bit arbitrary and is more for our human brain consumption than there's basically no strict difference between what's here and what's here. But I think it's kind of easier to present it and think about it this way. But you feel free to ignore this. Okay, so now once I have this, I add another module, and here I put in a list. So this is basically another shorthand. I like them, and this is to specify a chain. It's a compact way to specify a net chain inside the net graph. Of course, there's these are just containers, so you can arbitrarily nest them. You can have a chain in a graph in a change, like that famous video, like a bird in a bird, in a pig in a cow. I don't know, some crazy guy cooking a lot of stuff in an oven. Anyways, you can nest them, and here I'm just using the same dimensionality. This is why it's 15, and I just throw in some fancy nonlinearity. So I basically take this 15 dimensional vector. I do a linear combination of it, nonlinearity, linear combination, nonlinearity, and then I go down to 2 because I want to in the end get a probability vector. And okay, rule. This is a generic thing for neural networks. The output is arbitrarily sized. So if you want to do a prediction, you can say I want 2 numbers like the mean and the standard deviation of a normal distribution, or I want like the 4 coordinates for a bounding box, like center, like x, y, width, and height. Yeah, you basically shape the network into what you want to get out. So in this case, I want 2 probabilities, so I say the output is of length 2. This is constrained by my problem. And softmax, of course, is to make it actually a probability vector. Now, this is the graph, so I need a second argument. It's slightly more complicated. Because with the chain is obvious what the structure is always one after the other. In this case, I want to basically say that these 3 they have to go into this one, and this one has to go into this one. It's not too complicated. So if you look at this, you say this is quite simple. Each input goes into this. And if I click on this, I see, this is my old linear thingy, which goes into this. Sorry, this text is scaling a bit too much compared to the image. And the concatenation is going into this. You can always hover on top of these things. So the output of class, for example, is input 2 of my concatenation. The output of age is input 3 of my concatenation. So this is useful if you're a bit confused about, you're doing some non-commutative thing like division or subtraction, and you want to be sure, what is going to what. And so in this case, the concatenation is completely not really commutative in a sense, but it doesn't really matter if there is a first axis or a second axis, so we don't care. And then this is going into a chain, and if I click on this, I go into the chain, and this is arbitrarily nestable, so this is arbitrarily clickable. And you can, this is the last one. There's no more things, but you can, I could pile up more things here. And this is my classifier. And okay, so good thing I wrote it. I don't remember how many is this. Let's check it. Okay, this is like 1,000, roughly 1,000. So I'm using this. I'm randomizing it. Always good. Take drop is taking 800, dropping 800 elements. So I just put this into training and validation, of course using the same name. And now I'm given this is a fancier problem, I'm using fancier call to net train, Titanic net training. You see, training now is my data set and has no issues working with it because my ports of the network, they have the right name. Yeah, this is called sex, class, age, survivor status. So there's no issues using this data set. Yeah, it works automatically. I get my object out. My validation has the same format. Now I don't want to keep clicking stop or using the completely arbitrary amount of rounds. A round is how many times you see your 800 examples, or is also called epoch. I want to use something a bit fancier, so I'm using this training stopping criterion, so I can go and get a coffee. My criterion is loss. You could use an arbitrary metric. I could use F1 score, accuracy, or something like this. But I don't want to use. I want to stay like close to metal. So I'm saying like, let's use loss. And here I give 2 parameters: initial patience and patience. This means like for 100 iterations of a loss computation, don't do anything. Don't apply anything. Like ignore this criterion. After 100 iterations, check that loss is improving and wait 10 iterations before taking a decision. If after 10 iterations is not improving, stop. If it is still improving, then go on for 10 more iterations and check again. So this is kind of an internal way to automatically stop the training and not go, infinite time. If you specify a validation set, this criterion will automatically apply to the validation set because, of course, it makes more sense. If you don't specify a validation set, I believe we randomly select. I have to check in the documentation, but we randomly select like some percentage of a training set to compute the validation on, but it makes a bit less sense. What is all is basically this thing here is let's go to what is lesson. Let's use the documentation. So nettrain has net dataset or function. Now this is a nice way to use this, but not gonna cover it now. And property. So default property is the train network. I want to get all the properties nicely packaged together in this nettrain result object. So this is why I put all here. And then, okay, beside the criterion, I also want to get automatically some measurements. So I say, compute me the accuracy, the precision, the recall, and the error rate. So I already run this, so I'm not going to run it again. Oh, actually, this took 9 seconds, so I can actually do run it again. So you see, everything stuff is going down, blah blah blah. And you see, okay, done. So now you have a final loss, all my rounds, training validation. You see that this was very stable at the end, so it was a good. I could have stopped probably around here, but I wanted to go ahead a bit. This gives me the accuracy. So you see, like error rates on the validation, the accuracy is a bit like strictly lower than this. This is moving. Why is going so much up and down? Like a bit because we are changing the parameters every time, and a bit because we are selecting the data randomly every time. So you see this batch size is 64. So I have 800 examples in total, and I'm picking 64. So now, given that we don't have so many examples, one thing we can do is experiment a bit here. Batch size, let's say 256. With a very small network, we can just give more examples. Okay, so this stopped sooner because it moved more, and it got this is a bit worse. So I probably could have gone ahead a bit more, but yeah, not completely different. In general, if you can accommodate like a larger batch size, I would go high. Not as high as you can, but you get a bit more statistics in each mini batch if you add more examples. Well, the batch size, you can pick it based on the number of training examples, but the point is that you have, like if you have 100 million images, you don't really want to scale the batch size based on that. You scale your batch size based on the GPU memory that you have. So you tend to saturate your hardware resources with the batch, yeah. this is like a framework like TensorFlow has a nice name because it's actually a tensor flowing through all these operations. So the tensor gets bigger the more elements you have in the batch. Yeah, we don't show the batch dimension here, but the input here is a vector of size 2, and here 3, and here 1, so in total 5. But the actual, in the optimizer, the actual input is 5 times the number of examples. So if you have, I don't know, an image, 300 by 300. Let's see, it's too late for me. So let's say I have 300 by 300 by 3. So I have this amount of numbers, and then each one of them is let's say like a byte, but it's converted to real 32. So I get something like this. So each example has this size, and if I have 64 images, then like this is 500 megabytes. Yeah, so this is roughly the size of a tensor flowing through. And then depends, if you have like operations that are like n square, this goes up. You try to keep this number roughly stable. You don't want to inflate it too much. But you have some operational order n square in the network. So yeah, I mean, you don't want to go too crazy with the batch size because your memory will blow up. And also, this is why some very big networks you don't train at home. You train on a large cloud infrastructure where you can scale up the number of you can have like 100 GPUs there. Okay. Okay. Yeah. Well, now we've done the training, we can actually given that we have a trained network, we can take it. So here, for example, I take four example from my, let's switch random again, 4 random choices for my validation set. So it's a 3rd class, 13 years old male, this died, and okay, this is correct. This is correct, this is correct, this is correct. Okay, this was fine. This is okay, incorrect. Correct. Incorrect, incorrect. This batch was particularly bad. But yeah, in general, like 20% of the times, I will not predict the correct number. But yeah, I mean, this is a kind of a manual way to create a solver for the Titanic dataset problem. Now, what you see in the papers, they do like kind of ablation studies. So you say, okay, what if I use ramp instead of swish? What if I use more features? What if I use a deeper network here? Yeah, like a trend now, I mean, since a while, is to scale things together. Yeah, so I use like more features, a larger network, and a deeper network at the same time. Yeah, I scale all the dimensions together, and then you see how it performs. So we said like let's use things. Let's change the number of features a bit. Here, put some reference to our tutorials. I kind of said everything I want to say. Okay, so thank you guys. Bye-bye.